Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. Beneath the surface of the Earth, at a depth that varies from place to place and from season to season, there exists a boundary below which all the spaces between grains of rock and soil, all the tiny fractures in stone, and all the minute openings in geological formations are completely filled with water. This boundary is known as the water table, and it represents one of the most fundamental yet least observed features of the terrestrial landscape. The water table is not a fixed or rigid surface, but rather a gently undulating plane that rises and falls in response to precipitation, evaporation, the pumping of wells, and the slow and ceaseless movement of water through underground materials. It is estimated that approximately 30.1% of all the fresh water on the planet Earth is stored underground, amounting to roughly 10.6 million cubic kilometers of water held within the pores and fractures of subsurface rocks and sediments. This vast reservoir, known collectively as groundwater, dwarfs the volume of fresh water held in all the world's lakes, rivers, and streams combined, which together account for only about 0.3% of the total freshwater supply. The concept of the water table has been understood in practical terms for thousands of years, as the digging of wells has been a human activity since at least 6,500 BCE, when early wells were constructed in the Jezreel Valley of what is now modern-day Israel. These ancient well diggers understood, in their own way, that if one were to excavate downward through the soil, one would eventually reach a depth at which water began to seep into the hole from all directions. This depth, they recognized, varied with the seasons and with the distance from rivers and other bodies of surface water. What they could not have known, however, was the full extent of the hydrological system that lay beneath their feet, a system in which water moves through rock and sediment at rates ranging from mere centimeters per year to several meters per day, driven by the force of gravity and the differences in pressure that exist between one point underground and another. The water table itself is defined more precisely as the surface at which the pore water pressure is exactly equal to atmospheric pressure. Above the water table lies a region known as the vadose zone, or the unsaturated zone, in which the pore spaces contain both air and water. In this zone, water clings to the surfaces of soil grains and rock particles through the force of capillary action, and it moves predominantly downward under the influence of gravity, though some of it is drawn upward again by the roots of plants and returned to the atmosphere through the process of transpiration. Below the water table lies the saturated zone, sometimes referred to as the phreatic zone, in which every available pore space, fracture, and void is completely filled with water. It is within this saturated zone that the bulk of the world's groundwater is stored and through which it moves, however slowly, from areas of higher hydraulic head to areas of lower hydraulic head. The depth to the water table varies enormously depending on the local geology, the climate, the topography, and the patterns of human water use. In humid regions with abundant rainfall, the water table may lie within a meter or two of the surface, and in some low-lying areas or wetlands, it may actually intersect the surface, giving rise to springs, seeps, and standing bodies of water. In arid and semi-arid regions, by contrast, the water table may lie tens or even hundreds of meters below the surface. In parts of the Sahara Desert, for example, the water table has been measured at depths exceeding 300 meters, while in certain areas of the Arabian Peninsula, it may be found at depths of 100 to 200 meters below the ground surface. In the Great Plains of the United States, the depth to the water table in the Ogallala Aquifer ranges from less than 30 meters in parts of Nebraska to more than 120 meters in portions of Texas and New Mexico. The shape of the water table is influenced primarily by the topography of the overlying land surface, though the relationship is not one of simple correspondence. In general, the water table tends to be a subdued reflection of the surface topography, rising beneath hills and falling beneath valleys, though its undulations are less pronounced than those of the land surface above. This is because water that infiltrates into the ground beneath a hilltop must travel a greater horizontal distance to reach a discharge point, such as a stream or spring, than water that infiltrates nearer to a valley bottom. As a result, the water table beneath a hilltop stands at a higher elevation than the water table beneath a nearby valley. And the difference in elevation creates a hydraulic gradient that drives the slow lateral movement of groundwater from areas of recharge beneath the hills to areas of discharge in the valleys. The materials through which groundwater moves are classified according to two fundamental properties: porosity and permeability. Porosity is defined as the fraction of the total volume of a rock or sediment that is occupied by void spaces, or pores. It is typically expressed as a percentage, and it can range from less than 1% in dense, unfractured crystalline rocks such as granite to more than 50% in loosely packed, well-sorted sediments such as gravel or coarse sand. A typical sandstone might have a porosity of 10 to 20%, while a well-sorted sand deposit might have a porosity of 25 to 50%. Clay, despite its very high porosity, which can exceed 50% in some cases, holds water so tightly in its extremely small pore spaces that very little of it can flow freely, a distinction that leads to the concept of effective porosity, which is the fraction of the total porosity through which water can actually move. Permeability, on the other hand, is a measure of the ease with which a fluid can flow through a porous material. It depends not only on the total volume of pore space, but also on the size, shape, and interconnectedness of the individual pores. A rock or sediment with large, well-connected pores, such as a clean gravel or coarse sand, will have a high permeability, meaning that water can flow through it relatively easily. A material with very small or poorly connected pores, such as clay or unfractured shale, will have a very low permeability, meaning that water moves through it extremely slowly. The permeability of geological materials spans an enormous range, covering more than 12 orders of magnitude. Clean gravel may have a hydraulic conductivity, which is the measure of permeability most commonly used in hydrogeology, of approximately 1 to 1,000 meters per day. while intact clay may have a hydraulic conductivity of less than 0.0001 meters per day, or roughly 1 centimeter per century. The relationship between the rate of groundwater flow and the hydraulic gradient was first quantified in 1856 by a French engineer named Henry Darcy, who was working on the water supply system for the city of Dijon. Through a series of carefully controlled experiments involving the flow of water through columns of sand, Darcy established that the rate of flow is directly proportional to the hydraulic gradient and to the cross-sectional area through which the flow occurs, and that it is also proportional to a coefficient that characterizes the permeability of the material. This relationship, which has come to be known as Darcy's law, is expressed mathematically as Q equals K times A times the change in hydraulic head divided by the length of the flow path, where Q is the volumetric flow rate, K is the hydraulic conductivity, A is the cross-sectional area, and the ratio of the change in head to the length is the hydraulic gradient. Darcy's law remains one of the foundational equations of hydrogeology, and it is used to this day in virtually every calculation involving the movement of groundwater through porous media. It is worth noting that Darcy's law applies strictly to laminar flow, which is the type of slow, smooth, orderly flow that prevails in most groundwater settings. In situations where groundwater velocities are unusually high, such as in large fractures or in the conduits of karst limestone systems, the flow may become turbulent, and Darcy's law no longer provides an accurate description of the flow behavior. However, for the vast majority of groundwater systems, in which water moves at velocities measured in meters per year rather than meters per day, Darcy's law is an excellent approximation. The typical velocity of groundwater movement in a sandy aquifer, for instance, is on the order of 0.3 to 3 meters per day, while in a clay or silt formation, velocities may be as low as a few centimeters per year. In some deep sedimentary basins, groundwater has been shown by isotopic dating to have residence times of tens of thousands or even millions of years, indicating flow rates so slow as to be almost imperceptible on a human timescale. The geological formations that store and transmit significant quantities of groundwater are known as aquifers, a term derived from the Latin words aqua, meaning water, and fere, meaning to carry. Aquifers are broadly classified into two principal types, unconfined aquifers and confined aquifers. An unconfined aquifer, also known as a water table aquifer, is one in which the upper boundary of the saturated zone is the water table itself, and the water in the aquifer is in direct hydraulic connection with the atmosphere through the overlying unsaturated zone. In an unconfined aquifer, the water table is free to rise and fall in response to changes in the rate of recharge and discharge, and the position of the water table at any given time reflects the current balance between the water entering the aquifer from above and the water leaving it through wells, springs, and seepage into streams. A confined aquifer, by contrast, is one that is bounded above and below by relatively impermeable layers of rock or sediment, known as confining layers or aquitards. In a confined aquifer, The water is under pressure greater than atmospheric because the weight of the overlying confining layer and the water above it presses down upon the water in the aquifer. When a well is drilled into a confined aquifer, the water in the well rises above the top of the aquifer to a level known as the potentiometric surface, which is the level to which water would rise in a tightly cased well that penetrates the confined aquifer. If the potentiometric surface is above the ground surface at the location of the well, the water will flow out of the well under its own pressure, without the need for pumping. Such a well is known as a flowing artesian well, and the aquifer from which it draws is known as an artesian aquifer. The term artesian derives from the province of Artois in northern France, where flowing wells tapping a confined chalk aquifer were first documented in the year 1126. The phenomenon was regarded with considerable wonder at the time, as the water appeared to rise from the ground of its own accord, seemingly in defiance of the laws of gravity. It was not until the development of a more complete understanding of hydrostatic pressure in the 17th and 18th centuries that the mechanism behind artesian flow was properly understood. The key to the artesian phenomenon lies in the geometry of the confined aquifer system, the recharge area, where the aquifer is exposed at the surface and receives water from precipitation, must be at a higher elevation than the location of the well. The water that enters the aquifer at the recharge area flows down dip through the confined formation, and because it is trapped between impermeable layers, it cannot escape to the surface along the way. Instead, the pressure builds up along the length of the confined aquifer, and when a well punctures the confining layer, the accumulated pressure forces the water upward through the wellbore. One of the most famous artesian aquifer systems in the world is the Great Artesian Basin of Australia, which underlies approximately 1.7 million square kilometers of the Australian continent, covering parts of Queensland, New South Wales, South Australia, and the Northern Territory. The basin contains an estimated 64,900 cubic kilometers of groundwater, making it one of the largest underground freshwater reservoirs on Earth. The water-bearing formations of the Great Artesian Basin consist primarily of Jurassic and Cretaceous sandstones, which are confined between layers of mudstone and siltstone. The recharge areas are located along the eastern margin of the basin, in the elevated terrain of the Great Dividing Range, where rainfall infiltrates into the exposed sandstone formations. From there, the water moves slowly westward and southward through the confined aquifer, a journey that can take up to 2 million years. Isotopic analysis of the water extracted from deep wells in the western portions of the basin has yielded ages ranging from several 100,000 to nearly 2 million years, providing a vivid illustration of the extraordinarily slow pace at which groundwater can move through geological formations. The Ogallala Aquifer, also known as the High Plains Aquifer, is another of the world's great aquifer systems, underlying approximately 450,000 square kilometers of the Great Plains region of the United States, spanning parts of 8 states from South Dakota in the north to Texas in the south. The Ogallala Formation consists primarily of poorly consolidated sands, gravels, silts, and clays deposited by streams flowing eastward from the Rocky Mountains during the late Miocene and Pliocene epochs, roughly 2 to 6 million years ago. The aquifer is predominantly unconfined over most of its extent, and the water table within it has been declining steadily since large-scale irrigation pumping began in the 1940s and 1950s. In some areas, particularly in the southern portions of the aquifer in Texas and Kansas, the water table has dropped by more than 45 meters since the beginning of intensive pumping, and the saturated thickness of the aquifer has been reduced by more than 50%. The rate of recharge to the Ogallala aquifer is extremely low, averaging only about 15 to 25 millimeters per year over most of its area, which means that the water being pumped today was largely deposited thousands of years ago and is essentially a non-renewable resource on human timescales. The process by which water enters an aquifer from the surface is known as recharge, and it is one of the most critical factors governing the long-term sustainability of groundwater resources. Recharge occurs primarily through the infiltration of precipitation into the soil and its subsequent percolation downward through the unsaturated zone to the water table. The rate of recharge depends on a number of factors, including the amount and intensity of precipitation, the permeability of the surface soils, the depth to the water table, the slope of the land surface, the type and density of vegetation, and the rate of evapotranspiration. In humid temperate regions, recharge rates are typically on the order of 100 to 500 millimeters per year, which represents roughly 10 to 30% of the total annual precipitation. In semi-arid and arid regions, recharge rates may be as low as 1 to 10 millimeters per year, representing less than 1% of the total precipitation. Recharge can also occur through several other mechanisms besides direct infiltration of rainfall. One important mechanism is the recharge that occurs along the beds and banks of streams and rivers, particularly in arid regions where streams are often losing streams, meaning that the water table lies below the level of the stream bed and water seeps out of the stream and percolates downward to the water table. Another mechanism is the focused recharge that occurs through topographic depressions, such as playas, sinkholes, and dry lake beds, where surface water collects and has time to infiltrate into the subsurface. In urban areas, recharge can be enhanced by the leakage of water from water supply and sewer pipes, which has been estimated to contribute as much as 20 to 50% of the total recharge in some cities. Artificial recharge, in which water is deliberately introduced into the ground through injection wells, infiltration basins, or spreading grounds, is also practiced in many parts of the world as a means of replenishing depleted aquifers and storing water underground for future use. The movement of groundwater from areas of recharge to areas of discharge constitutes what is known as a groundwater flow system. In the simplest case, a local flow system carries water from a recharge area on a topographic high to a discharge area in a nearby valley or along a stream. The flow path is relatively short, the travel time is relatively brief, and the water that discharges may be only a few years or decades old. At a larger scale, Intermediate flow systems carry water over greater distances, passing beneath one or more topographic highs and lows before discharging at a more distant point. And at the largest scale, regional flow systems carry water from major recharge areas, such as mountain ranges or extensive upland plateaus, to distant discharge points, such as major river valleys or coastal areas. The travel times in regional flow systems can be extremely long, ranging from hundreds to millions of years, and the water that discharges from these systems may have entered the ground during entirely different climatic periods, when the patterns of precipitation and temperature were markedly different from those that prevail today. The concept of nested flow systems, in which local, intermediate, and regional flow systems are superimposed upon one another in the same aquifer, was first described in detail by the Hungarian-Canadian hydrogeologist Joseph Toth in 1963. Toth's theoretical analysis showed that even in a simple, homogeneous aquifer with a gently undulating water table, the pattern of groundwater flow could be quite complex, with multiple flow cells of different sizes nested within one another like a set of Russian dolls. The practical implications of Toth's work were significant, because it demonstrated that the quality and temperature of groundwater could vary substantially from one location to another, even within the same aquifer, depending on which flow system a particular well or spring was tapping. The discharge of groundwater to the surface occurs through several mechanisms, the most visible of which is the emergence of springs. A spring is defined as a point at which groundwater flows naturally to the surface of the earth. Springs can be classified in a variety of ways, including by the mechanism of their formation, by the magnitude of their flow, and by the temperature and chemical composition of their water. Contact springs form where a permeable formation, such as a sandstone or gravel, overlies an impermeable formation, such as a clay or shale, and the water that has been moving through the permeable layer is forced to the surface at the contact between the two formations. Fault springs occur where a fault has brought a permeable formation into contact with an impermeable formation, creating a pathway for groundwater to reach the surface along the fault plane. Karst springs, which are among the largest and most spectacular springs in the world, occur where groundwater that has been flowing through the dissolved cavities and conduits of a limestone or dolomite aquifer emerges at the surface. The largest springs in the world can discharge truly enormous volumes of water. The spring of the Vaucluse, or Fontaine de Vaucluse, in southeastern France, is one of the largest karst springs in Europe, with an average discharge of approximately 21 cubic meters per second, though its flow can vary from a mere trickle in dry periods to more than 100 cubic meters per second during major flood events. In the United States, the springs of Florida are among the most prolific in the world, owing to the highly karstified nature of the Floridan aquifer, which underlies the entire state and much of the adjacent coastal plain. Silver Springs, near Ocala, Florida, has an average discharge of approximately 22 cubic meters per second, while the combined flow of the first magnitude springs in Florida exceeds 350 cubic meters per second. These springs are the surface expression of vast underground drainage systems that have been carved over millions of years by the slow dissolution of limestone by slightly acidic groundwater. The process by which limestone is dissolved to form karst landscapes is a particularly noteworthy aspect of groundwater hydrology. Limestone is composed primarily of calcium carbonate, which is only very slightly soluble in pure water. However, when rainwater absorbs carbon dioxide from the atmosphere and from the decomposition of organic matter in the soil, it becomes a weak solution of carbonic acid, with a pH typically ranging from about 5.5 to 6.5. This slightly acidic water is capable of slowly dissolving calcium carbonate, a process that can be represented by the chemical equation in which calcium carbonate reacts with water and carbon dioxide to produce calcium ions and bicarbonate ions in solution. Over thousands and millions of years, this process of dissolution creates an intricate network of enlarged fractures, tubes, conduits, and caverns within the limestone, through which groundwater can flow at rates far exceeding those possible in ordinary porous media. Karst landscapes are found on every continent and are estimated to underlie approximately 15 to 20% of the Earth's ice-free land surface. Some of the most extensive karst regions include the Dinaric karst of the Western Balkans, which lends its name to the entire category of terrain, the karst regions of southern China, the Yucatan Peninsula of Mexico, the karst plateaus of central and southern Italy, and the limestone regions of the Midwestern and southeastern United States. In karst regions, the water table concept becomes somewhat more complicated because the flow of water through large conduits and caverns does not conform to the assumptions of Darcy's law, which was developed for flow through porous, granular media. In a karst aquifer, the water may exist in two distinct domains: the water stored in the tiny pores and fractures of the rock matrix, which behaves much like groundwater in any other type of aquifer, and the water flowing rapidly through the large conduits and caves, which behaves more like surface water, with turbulent flow, rapid travel times, and direct connections to the surface through sinkholes and sinking streams. The vulnerability of karst aquifers to contamination is a matter of considerable concern, because the large conduits and direct connections to the surface that characterize karst systems can allow contaminants to reach the groundwater very quickly, with little or no filtration or attenuation. In a typical porous media aquifer, such as a sand or gravel formation, a contaminant that is introduced at the surface must pass through the unsaturated zone and then move through the tiny pore spaces of the aquifer material before it reaches a well or spring. During this passage, the contaminant may be filtered out by the small pore spaces, adsorbed onto the surfaces of soil and rock particles, broken down by chemical reactions, or consumed by microorganisms. In a karst aquifer, by contrast, a contaminant that enters a sinkhole or a sinking stream can be transported directly into the conduit system and carried rapidly to a spring or well, covering distances of several kilometers in a matter of hours or days, with virtually no filtration or attenuation along the way. This is why karst springs are often among the first water sources to show the effects of surface contamination, and why the protection of recharge areas and karst regions is considered to be of paramount importance. The contamination of groundwater, whether in karst or non-karst settings, is one of the most serious environmental challenges of the modern era. Groundwater contamination can result from a wide variety of sources, including the disposal of industrial wastes, the application of agricultural chemicals, the leakage of underground storage tanks, the improper disposal of household hazardous wastes, the seepage of contaminated surface water, and the intrusion of salt water into coastal aquifers. Once a contaminant enters the groundwater system, it can persist for decades or centuries because the slow rate of groundwater movement means that the contaminated water may take a very long time to flush through the system and be replaced by clean water. The remediation of contaminated groundwater is technically difficult and extremely expensive, with costs that can run into the hundreds of millions of dollars for a single contaminated site, and in many cases, complete remediation is not technically feasible. Among the most common groundwater contaminants are nitrate, which is derived primarily from agricultural fertilizers and animal wastes, and which can cause methemoglobinemia, or blue baby syndrome, in infants when present in drinking water at concentrations above 10 milligrams per liter as nitrogen. Volatile organic compounds such as trichloroethylene, tetrachloroethylene, and benzene, which are used as industrial solvents and degreasers, are another widespread class of groundwater contaminants. These compounds are particularly problematic because they are denser than water and can sink to the bottom of an aquifer, forming pools of undissolved liquid known as dense non-aqueous phase liquids, or DNAPLs, which can slowly dissolve into the groundwater and contaminate large volumes of the aquifer over many years. Petroleum hydrocarbons, including gasoline and diesel fuel, are also common groundwater contaminants, particularly in the vicinity of gas stations, fuel storage depots, and petroleum refineries. Unlike the chlorinated solvents, petroleum hydrocarbons are lighter than water and tend to float on the water table as a thin layer of free product, from which dissolved components can migrate into the underlying groundwater. The intrusion of salt water into freshwater aquifers is a particularly significant problem in coastal regions, where the boundary between fresh groundwater and the saline water of the ocean is maintained by a delicate balance of pressures. Under natural conditions, the fresh groundwater, which is less dense than salt water, floats on top of the underlying salt water in a relationship that was first described mathematically by the Dutch scientist Baron GHJBN in 1888 and independently by the German scientist Herzberg in 1901. According to the GHJBN-Herzberg relation, for every meter of freshwater head above sea level, the interface between the freshwater and the saltwater extends approximately 40 meters below sea level. This means that if the water table in a coastal aquifer is 2 meters above sea level, the freshwater zone extends to approximately 80 meters below sea level, below which the water is saline. When pumping from a coastal well lowers the water table, the saltwater interface rises in response, and if the pumping is excessive, the saltwater can be drawn upward into the well, rendering the water unpotable. This process, known as saltwater intrusion or saltwater upconning, has affected coastal aquifers in many parts of the world, including the coastal regions of Florida, California, the Netherlands, Israel, and Bangladesh. The chemical composition of groundwater is determined by a variety of factors, including the composition of the precipitation that provides the recharge, the mineralogy of the rocks and sediments through which the water passes, the length of time the water has been in contact with the aquifer materials, and the biological processes that occur in the subsurface. As groundwater moves through an aquifer, it gradually dissolves minerals from the surrounding rock, acquiring a chemical signature that reflects the composition of the aquifer material. In a limestone aquifer, for example, the groundwater will be enriched in calcium and bicarbonate, while in a sandstone aquifer cemented with silica, the water may be enriched in dissolved silica. In aquifers containing evaporite minerals, such as gypsum or halite, the groundwater may have very high concentrations of sulfate, calcium, sodium, and chloride, rendering it unsuitable for drinking or irrigation without treatment. The temperature of groundwater also varies depending on the depth from which it is drawn and the local geothermal gradient. Near the surface, groundwater temperatures closely approximate the mean annual air temperature of the region, which in temperate climates is typically between 8 and 15 degrees Celsius. At greater depths, the temperature increases in accordance with the geothermal gradient, which averages approximately 25 to 30 degrees Celsius per kilometer of depth, though it can be considerably higher in areas of active volcanism or geothermal activity. Hot springs and geysers, such as those found in Yellowstone National Park in the United States, in Iceland, and in the Taupo volcanic zone of New Zealand, are the surface expression of groundwater that has been heated by contact with magma or hot rock at depth. The water that erupts from Old Faithful Geyser in Yellowstone, for instance, has been heated to temperatures exceeding 200 degrees Celsius at depth, and the eruption is driven by the sudden conversion of superheated water to steam as the pressure is released. The study of groundwater and the water table has been formalized as the scientific discipline of hydrogeology, which draws upon principles from geology, physics, chemistry, biology, and mathematics to understand the occurrence, movement, and quality of water in the subsurface. The foundations of modern hydrogeology were laid in the 19th century by workers such as Darcy, whose law has already been mentioned, and by the French engineer Jules Dupuit, who in 1863 published a theoretical analysis of groundwater flow to wells that remains in use today. Dupuit's analysis, which assumed that the flow to a well in an unconfined aquifer is horizontal and that the hydraulic gradient at any point is equal to the slope of the water table, provided a simple and reasonably accurate method for calculating the rate at which water could be pumped from a well without lowering the water table below a specified level. In the 20th century, The development of hydrogeology was greatly advanced by the work of the American hydrologist Charles Vernon Tice, who in 1935 published a groundbreaking paper on the response of a confined aquifer to pumping. Tice recognized that when a well begins pumping from a confined aquifer, the drawdown of the potentiometric surface propagates outward from the well as a cone of depression, which expands over time in a manner analogous to the way heat spreads through a solid. By drawing upon the mathematical analogy between groundwater flow and heat conduction, Tice derived an equation, now known as the Tice equation, that describes the drawdown at any distance from a pumping well as a function of time, pumping rate, transmissivity, and storativity. The Tice equation was a major advance because it allowed hydrogeologists to predict the effects of pumping on the water levels in an aquifer and to determine the hydraulic properties of the aquifer from pumping test data. The cone of depression that forms around a pumping well is a feature of considerable practical importance. When a well begins to pump, the water level in the well drops below the surrounding water table or potentiometric surface, creating a hydraulic gradient that causes water to flow toward the well from all directions. As pumping continues, the cone of depression deepens and widens, extending outward from the well until it reaches a source of recharge, such as a stream or a recharge boundary, or until a new equilibrium is established between the rate of pumping and the rate at which water flows into the cone of depression. In heavily pumped aquifers, the cones of depression from adjacent wells may overlap, causing the water table or potentiometric surface to decline over a broad area. This phenomenon, known as regional drawdown, has been observed in many of the world's most intensively exploited aquifer systems, including the Ogallala Aquifer in the United States, the North China Plain Aquifer in China, and the Punjab Aquifer in India and Pakistan. The global significance of groundwater as a resource for human use cannot be overstated. It is estimated that approximately 2.5 billion people worldwide depend on groundwater as their primary source of drinking water, and that groundwater provides approximately 43% of the water used for irrigation worldwide. In the United States, groundwater supplies approximately 26% of the total freshwater withdrawals and serves as the primary source of drinking water for approximately 130 million people. In many parts of the developing world, groundwater is the only reliable source of water available year-round, as surface water sources may be seasonal or contaminated. The total global rate of groundwater withdrawal has been estimated at approximately 982 cubic kilometers per year as of 2010, and in many regions, the rate of withdrawal exceeds the rate of natural recharge, leading to the progressive depletion of groundwater reserves and the decline of water tables. The decline of water tables due to excessive pumping is one of the most pressing water resource challenges of the 21st century. In the North China Plain, which produces approximately 1/4 of China's grain harvest, the water table has been falling at a rate of 1 to 3 meters per year in some areas, and the deep aquifer has experienced declines of more than 50 meters since the 1960s. In India, which is the world's largest user of groundwater, pumping approximately 251 cubic kilometers per year. The water table has fallen dramatically in many states, particularly in Punjab, Haryana, Rajasthan, and Tamil Nadu. In the Ogallala Aquifer region, as previously mentioned, decades of intensive pumping have reduced the saturated thickness of the aquifer by more than 50% in some areas, and it has been estimated that at current rates of extraction, large portions of the aquifer could be effectively depleted within 25 to 50 years. The consequences of groundwater depletion extend beyond the simple reduction of water supplies. As the water table declines, the cost of pumping increases because each additional meter of drawdown requires more energy to lift the water to the surface. This can render irrigation economically unviable in some areas, forcing farmers to switch to less water-intensive crops or to abandon cultivation altogether. Groundwater depletion can also cause the land surface to subside, as the removal of water from the pore spaces allows the aquifer materials to compact under the weight of the overlying sediments. Land subsidence due to groundwater pumping has been documented in many parts of the world, including the Central Valley of California, where cumulative subsidence of more than 8.5 meters was measured at one location between 1925 and 1977, the Mexico City metropolitan area, where subsidence of up to 9 meters has occurred since the early 20th century, and the city of Bangkok, Thailand, where subsidence of up to 1 meter has been measured. Once the aquifer materials have compacted, the loss of storage capacity is largely irreversible, meaning that even if the water table is allowed to recover, the aquifer can never store as much water as it did before the compaction occurred. Another consequence of groundwater depletion is the reduction of base flow to streams and rivers. In many regions, a significant portion of the flow in streams and rivers during dry periods is derived from the discharge of groundwater, which seeps into the stream channel through the streambed and banks. This component of stream flow, known as base flow, is essential for maintaining aquatic ecosystems, supporting downstream water users, and diluting pollutants. When the water table declines below the level of the streambed, the stream loses its connection to the groundwater system and may cease to flow during dry periods, a phenomenon that has been observed with increasing frequency in many parts of the world as groundwater pumping has intensified. The interaction between groundwater and surface water is a topic that has received increasing attention from hydrologists and ecologists in recent decades, as it has become clear that the two systems are intimately connected and that the management of one cannot be separated from the management of the other. Streams can be classified as either gaining streams, in which groundwater discharges into the stream and contributes to its flow, or losing streams, in which water seeps out of the stream and percolates downward to the water table. Many streams alternate between gaining and losing conditions along their length, depending on the local relationship between the stream stage and the water table elevation. In humid regions, most perennial streams are predominantly gaining streams, receiving a continuous supply of groundwater that sustains their flow even during dry periods. In arid regions, many streams are losing streams for most of their length, and the water that seeps out of the streambed provides an important source of recharge to the underlying aquifer. The unsaturated zone, or vadose zone, which lies between the land surface and the water table, plays a critical role in the hydrological cycle as the pathway through which recharge must pass before reaching the saturated zone. The vadose zone is a complex environment in which water, air, and solid particles coexist in intimate contact, and in which a variety of physical, chemical, and biological processes act to modify the quantity and quality of the water as it moves downward. The movement of water through the unsaturated zone is governed by a combination of gravitational and capillary forces, and it can be described mathematically by the Richards equation, which was formulated by the American physicist Lorenzo Adolph Richards in 1931. The Richards equation is a highly nonlinear partial differential equation, and its solution requires detailed knowledge of the relationships between the water content, the capillary pressure, and the hydraulic conductivity of the soil. Relationships that are collectively known as the soil-water characteristic curves or soil-water retention curves. Within the vadose zone, a phenomenon known as the capillary fringe exists immediately above the water table. The capillary fringe is a zone in which the pore spaces are fully saturated with water, but the water pressure is less than atmospheric. The water in the capillary fringe is held above the water table by capillary forces, which are the same forces that cause water to rise in a narrow tube against the force of gravity. The height of the capillary fringe depends on the pore size of the material. In coarse sands and gravels, the capillary fringe may be only a few centimeters thick, while in fine-grained silts and clays, it can extend to heights of more than 2 meters above the water table. The capillary fringe is of practical significance because it can affect the accuracy of water table measurements made in shallow wells and piezometers, and because it represents a zone of transition between the unsaturated and saturated conditions that must be accounted for in models of subsurface flow and transport. The geological context in which groundwater occurs is as varied as the geology of the Earth itself. In unconsolidated sedimentary deposits, such as the alluvial fills of river valleys, the glacial deposits of the northern continents, and the coastal plain sediments of passive continental margins, groundwater is stored and transmitted through the intergranular pore spaces between the individual grains of sand, silt, gravel, and clay. These deposits often form highly productive aquifers because their porosity and permeability are relatively high, and they are frequently located in areas of abundant recharge. The alluvial aquifers of the major river valleys, such as the Mississippi, the Ganges, the Mekong, and the Nile, are among the most important groundwater resources in the world, supplying water for drinking, irrigation, and industrial use to hundreds of millions of people. In consolidated sedimentary rocks, such as sandstones, limestones, and dolomites, groundwater is stored in the primary pore spaces of the rock, in fractures and joints, and in the dissolution cavities that form insoluble rocks. Sandstone aquifers are among the most common and most productive aquifer types worldwide because sandstones typically have moderate to high porosity and permeability, and because they are widespread in the sedimentary basins that underlie much of the world's land area. The Nubian sandstone aquifer, which underlies portions of Libya, Egypt, Sudan, and Chad, is one of the largest aquifer systems in the world, containing an estimated 150,000 cubic kilometers of groundwater, most of which was recharged during humid climatic periods thousands of years ago and is now essentially fossil water. In crystalline rocks such as granites, gneisses, and schists, the primary porosity is typically very low, often less than 1%. And the ability of these rocks to store and transmit groundwater depends almost entirely on the presence of fractures and weathered zones. The uppermost portion of a crystalline rock body is often intensely weathered, producing a layer of saprolite or decomposed rock that can have porosities of 20 to 40% and can function as a shallow aquifer. Beneath the saprolite, the competent bedrock may contain networks of interconnected fractures that can transmit significant quantities of water, particularly where the fractures have been enlarged by dissolution or tectonic activity. In many parts of sub-Saharan Africa, South Asia, and South America, crystalline rock aquifers are an important source of water for rural communities, although the yields of individual wells in these formations tend to be modest, typically ranging from 0.5 to 5 liters per second. Volcanic rocks present yet another geological context for groundwater occurrence. Basaltic lava flows, such as those that make up the Columbia Plateau of the northwestern United States and the Deccan Traps of India, can be highly productive aquifers. Because the contacts between individual lava flows are often characterized by zones of high permeability, including vesicular zones, rubble zones, and interflow sedimentary layers. The Columbia Plateau Regional Aquifer System, which underlies approximately 163,000 square kilometers of Washington, Oregon, and Idaho, is one of the most productive basalt aquifer systems in the world, yielding water to wells at rates of up to 100 liters per second in some areas. In the Hawaiian Islands, the basaltic lava flows that make up the volcanic edifices contain prolific aquifers that are recharged by the abundant rainfall on the windward sides of the islands. The basal water lens, which floats on the underlying salt water in accordance with the GHJBN-Herzberg principle, is the primary source of fresh water for the islands, and its management requires careful attention to the balance between recharge and pumping to avoid saltwater intrusion. The glacial deposits that blanket much of northern Europe, Northern Asia, and northern North America are another important geological setting for groundwater. These deposits, which were laid down during the Pleistocene ice ages, between approximately 2.6 million and 11,700 years ago, consist of a complex mixture of materials, including till, which is an unsorted mixture of clay, silt, sand, gravel, and boulders deposited directly by glacier ice, and outwash, which is stratified sand and gravel deposited by meltwater streams flowing away from the glacier front. The outwash deposits, with their high porosity and permeability, form some of the most productive aquifers in the glaciated regions, while the till deposits, with their low permeability, often serve as confining layers that separate the outwash aquifers from one another. The complexity of glacial stratigraphy, with its intricate layering of till and outwash in patterns that reflect the multiple advances and retreats of the glaciers, makes the characterization of glacial aquifer systems one of the more challenging tasks in hydrogeology. The measurement and monitoring of the water table is accomplished through a variety of techniques, the simplest and most direct of which is the measurement of the water level in a well or piezometer. A piezometer is a small diameter well that is open only at the bottom and that measures the hydraulic head at a specific point in the aquifer. By installing a network of piezometers at different locations and at different depths, hydrogeologists can construct maps of the water table or potentiometric surface that reveal the direction and magnitude of the hydraulic gradients that drive groundwater flow. In the United States, the United States Geological Survey maintains a network of more than 20,000 observation wells that are monitored regularly to track changes in groundwater levels over time. Similar monitoring networks exist in many other countries, and the data they provide are essential for understanding the long-term trends in groundwater availability and for making informed decisions about water resource management. In addition to direct measurements in wells, a number of remote sensing and geophysical techniques can be used to estimate the depth to the water table and the properties of the aquifer. Electrical resistivity surveys, in which an electrical current is passed through the ground and the resulting voltage differences are measured at the surface, can be used to identify the boundary between the unsaturated zone, which has a relatively high electrical resistivity, and the saturated zone, which has a relatively low resistivity. Ground-penetrating radar, which transmits pulses of electromagnetic energy into the ground and records the reflections from subsurface interfaces, can also be used to detect the water table in some settings, particularly where the unsaturated zone consists of sandy or gravelly materials with low electrical conductivity. The Gravity Recovery and Climate Experiment, or GRACE, a pair of satellites launched by NASA in 2002, has revolutionized the study of large-scale groundwater changes by measuring the tiny variations in the Earth's gravitational field that result from changes in the distribution of mass, including the mass of groundwater. By analyzing the GRACE data, researchers have been able to estimate the rate of groundwater depletion in major aquifer systems around the world, including the Ogallala, the North China Plain, the Ganges-Brahmaputra, and the Arabian Peninsula aquifers. The water table fluctuates on a variety of timescales, from daily and seasonal to decadal and longer. On a daily timescale, the water table may fluctuate by a few centimeters in response to changes in atmospheric pressure, the effects of earth tides, and the transpiration of water by plants during daylight hours. The effect of plant transpiration on the water table is particularly notable in areas where the water table is shallow and the vegetation has deep roots that can draw water directly from the saturated zone. In such settings, The water table may decline by several centimeters during the day as the plants transpire water, and then recover during the night when transpiration ceases, producing a characteristic diurnal pattern of water table fluctuation that was first described by the American hydrologist Walter White in 1932. On a seasonal timescale, the water table typically rises during the wet season, when recharge from precipitation exceeds discharge through springs, seepage, and pumping, and falls during the dry season, when discharge exceeds recharge. The amplitude of the seasonal fluctuation depends on the climate, the aquifer properties, and the patterns of water use, but it is typically on the order of 0.5 to 3 meters in temperate and humid regions. In some semi-arid regions, the seasonal fluctuation can be much larger, with the water table rising by 5 to 10 meters or more during the rainy season and falling by a similar amount during the dry season. On longer timescales, the water table responds to changes in climate, land use, and water management practices. Over the past century, the water table has declined significantly in many parts of the world due to the expansion of irrigated agriculture and the growth of urban water demand. At the same time, in some areas, the water table has risen due to changes in land use, such as the replacement of deep-rooted native vegetation with shallow-rooted crops or the irrigation of arid lands, which can introduce more water into the ground than was previously available through natural recharge. Rising water tables can cause problems of their own, including waterlogging of agricultural soils, salinization of the root zone, damage to building foundations, and the flooding of basements and underground infrastructure. The concept of sustainable yield, which refers to the rate at which water can be withdrawn from an aquifer without causing unacceptable environmental, economic, or social consequences, is central to the management of groundwater resources. The sustainable yield of an aquifer is not simply equal to the rate of natural recharge, as was once commonly assumed, because any withdrawal of groundwater must ultimately be balanced either by a reduction in the natural discharge of the aquifer, such as a decrease in the flow of springs and base flow to streams, or by an increase in the rate of recharge, such as might occur when the lowering of the water table induces additional infiltration from surface water bodies. The determination of sustainable yield requires a comprehensive understanding of the entire groundwater system, including its recharge areas, its discharge areas, its flow paths, its storage capacity, and its connections to surface water and ecosystems. The legal and regulatory frameworks governing groundwater use vary widely from one jurisdiction to another and reflect the different traditions, values, and hydrological conditions of different regions. In the western United States, groundwater rights are generally governed by the doctrine of prior appropriation, which allocates water to users based on the date of their first use, with earlier users having priority over later users in times of shortage. In the eastern United States, groundwater rights are more commonly governed by the riparian doctrine, which grants reasonable use of groundwater to the owners of the overlying land. In many countries, groundwater is considered to be the property of the state, and its use is regulated through a system of permits or licenses. The challenge of managing a resource that is hidden from view, that moves slowly across property boundaries and political jurisdictions, and that is accessed by millions of individual users acting independently, is one of the most difficult problems in water resource governance. The science of groundwater hydrology continues to advance, driven by new technologies, new theoretical insights, and the growing urgency of water resource challenges. Numerical models of groundwater flow and transport, which solve the governing equations on a discretized representation of the aquifer, have become indispensable tools for understanding and managing groundwater systems. The most widely used groundwater flow model is ModFlow, developed by the United States Geological Survey in the 1980s and continuously updated and improved since then. ModFlow uses a finite difference method to solve the groundwater flow equation in 3 dimensions, and it can simulate a wide variety of hydrogeological conditions, including unconfined and confined flow, flow to wells, interaction with surface water, and the effects of recharge and evapotranspiration. More advanced models, such as those that couple groundwater flow with solute transport, density-dependent flow, or reactive chemistry, are used to address more complex problems, such as the fate and transport of contaminants, the behavior of saltwater intrusion, and the geochemistry of natural and contaminated groundwater systems. The isotopic composition of groundwater provides another powerful tool for understanding the origin, age, and movement of water in the subsurface. The stable isotopes of hydrogen and oxygen, deuterium and oxygen, 18, are fractionated by the processes of evaporation and condensation, and the isotopic composition of precipitation varies systematically with latitude, altitude, temperature, and the distance from the ocean. By measuring the isotopic composition of groundwater and comparing it with the local precipitation, hydrogeologists can determine whether the water was recharged locally or at a distant location, and whether it was recharged under the current climatic conditions or under the different conditions that prevailed during past climatic periods. The radioactive isotopes of hydrogen and carbon, tritium and carbon-14, can be used to estimate the age of groundwater. Tritium, which has a half-life of 12.32 years, was introduced into the atmosphere in large quantities by nuclear weapons testing in the 1950s and 1960s, and its presence in groundwater indicates that the water was recharged at least in part after 1952. Carbon-14, which has a half-life of 5,730 years, can be used to date groundwater with ages up to approximately 40,000 years. Older groundwater, with ages ranging from tens of thousands to millions of years, can be dated using other isotopic systems, such as chlorine, 36, which has a half-life of 301,000 years, or krypton, 81, which has a half-life of 229,000 years. The role of groundwater in the global water cycle is often underappreciated, but it is of fundamental importance. Groundwater discharge to the oceans, which occurs both as direct submarine discharge through the seafloor and as indirect discharge through rivers and streams that receive base flow from aquifers, has been estimated at approximately 2,200 cubic kilometers per year, which is roughly 6% of the total river discharge to the oceans. Although this is a relatively small fraction of the total hydrological flux, submarine groundwater discharge can have significant ecological effects in coastal waters because the groundwater often carries elevated concentrations of nutrients, such as nitrogen and phosphorus, which can stimulate the growth of algae and contribute to the eutrophication of coastal ecosystems. Groundwater also plays an important role in maintaining the health of terrestrial ecosystems, particularly in arid and semi-arid regions where surface water is scarce. Many species of plants, known as phreatophytes, have evolved deep root systems that can tap into the water table and draw water directly from the saturated zone. These plants, which include species such as mesquite, tamarisk, cottonwood, and willow, are often found along river corridors and in areas where the water table is within a few meters of the surface. The health and distribution of these phreatophytic plant communities are closely linked to the depth and stability of the water table, and the decline of the water table due to excessive pumping can cause the dieback of these communities, with cascading effects on the wildlife that depends on them for habitat and food. The thermal properties of groundwater have long been exploited for human benefit. The use of geothermal springs for bathing and heating dates back thousands of years, with early examples found in the hot springs of Japan, Iceland, and the Roman Empire. In modern times, groundwater heat pump systems, also known as ground source heat pump systems, have emerged as an efficient and environmentally friendly technology for heating and cooling buildings. These systems take advantage of the fact that the temperature of the ground below the frost line remains relatively constant throughout the year, typically between 10 and 16 degrees Celsius in temperate climates. By circulating a fluid through a loop of buried pipes or through an open-loop system that draws groundwater from a well and returns it to the ground, a heat pump can extract heat from the ground in winter for space heating and reject heat to the ground in summer for air conditioning. The efficiency of ground source heat pump systems is typically 300 to 500%, meaning that they deliver 3 to 5 units of heating or cooling energy for every unit of electrical energy consumed, which is significantly more efficient than conventional heating and cooling systems. The phenomenon of land subsidence caused by groundwater withdrawal deserves further examination, as it is a problem that affects many of the world's largest and most economically important cities. In addition to the examples of California's Central Valley, Mexico City, and Bangkok mentioned earlier, significant subsidence has been documented in cities such as Venice, Italy, where subsidence of approximately 23 centimeters occurred between 1950 and 1970 due to industrial groundwater pumping, contributing to the flooding problems for which the city is famous, Jakarta, Indonesia, where subsidence of up to 25 centimeters per year has been measured in some areas, making it one of the fastest sinking cities in the world, and Shanghai, China, where cumulative subsidence of more than 2.6 meters has occurred since the early 20th century. In many of these cases, the subsidence was halted or slowed after the source of the problem was identified and groundwater pumping was reduced or relocated, but the damage to buildings, infrastructure, and flood protection systems was already done and could not be reversed. The process of aquifer storage and recovery, or ASR, represents an innovative approach to water management that takes advantage of the natural storage capacity of aquifers. In an ASR system, surplus water that is available during wet periods or periods of low demand is injected into an aquifer through a well for storage and is later recovered from the same well during dry periods or periods of high demand. The aquifer essentially functions as an underground reservoir, with the advantages that it is not subject to evaporative losses, does not require the construction of expensive surface storage facilities, and is protected from many forms of contamination. ASR has been practiced in various parts of the world since the 1960s, with notable examples in Florida, where numerous ASR systems have been developed to store treated drinking water, reclaimed wastewater, and stormwater for later use, and in the Netherlands, where ASR is used to store freshwater in brackish or saline aquifers for use during dry periods. The concept of managed aquifer recharge, or MAR, encompasses a broader range of techniques for intentionally recharging aquifers, including spreading basins, infiltration galleries, percolation ponds, dry wells, and riverbank filtration. These techniques are used for a variety of purposes, including the augmentation of water supplies, the improvement of water quality through natural filtration and attenuation, the creation of hydraulic barriers to prevent saltwater intrusion, and the maintenance of environmental flows in streams and wetlands. In arid and semi-arid regions, where the demand for water often exceeds the available supply, managed aquifer recharge is increasingly recognized as a critical tool for water security. In the city of Orange County, California, for example, the groundwater replenishment system, which began operating in 2008, treats wastewater to a very high standard using microfiltration, reverse osmosis, and ultraviolet disinfection, and then injects the treated water into the local aquifer to replenish the groundwater supply and prevent saltwater intrusion. The system has a capacity of approximately 380,000 cubic meters per day, making it one of the largest water recycling facilities in the world. The study of the water table and groundwater hydrology also intersects with the field of geochemistry in a number of important ways. The dissolved mineral content of groundwater tends to increase along the flow path as the water has more time to interact with the aquifer materials and dissolve their constituent minerals. This progressive increase in dissolved solids, known as the chemical evolution of groundwater, was described systematically by the Russian hydrogeochemist Alexander Chebotarev in 1955, who observed that the dominant anion in groundwater tends to change from bicarbonate near the recharge area to sulfate at intermediate positions along the flow path to chloride in the deepest and most distal portions of the flow system. This sequence, known as the Chebydarov sequence, reflects the relative solubilities of the common rock-forming minerals and provides a useful framework for understanding the chemical composition of groundwater in different parts of a flow system. The redox conditions of groundwater, which describe the balance between oxidizing and reducing chemical reactions, have a profound effect on the chemistry of the water and on the fate and transport of many contaminants. Near the water table, in the uppermost part of the saturated zone, groundwater is typically oxic, meaning that dissolved oxygen is present at concentrations of several milligrams per liter. As the water moves deeper into the aquifer and along longer flow paths, the dissolved oxygen is gradually consumed by the oxidation of organic matter and reduced minerals, and the water becomes progressively more reducing. In strongly reducing groundwater, iron and manganese are mobilized from the aquifer materials and dissolved in the water, often at concentrations that exceed drinking water standards and that can cause aesthetic problems such as staining and metallic taste. The redox conditions also control the speciation and mobility of many contaminants, including arsenic, chromium, uranium, and selenium, which can be either more or less mobile depending on the redox state of the groundwater. The natural occurrence of arsenic in groundwater is a major public health concern that affects tens of millions of people worldwide. In Bangladesh and the Indian state of West Bengal, the drinking water of an estimated 35 to 77 million people is contaminated with arsenic at concentrations exceeding the World Health Organization guideline value of 10 micrograms per liter. The arsenic is of natural origin, derived from the weathering of arsenic-bearing minerals in the sediments deposited by the Ganges-Brahmaputra river system. Under the reducing conditions that prevail in the shallow aquifers of the region, arsenic is released from the sediments into the groundwater, where it accumulates to concentrations that can exceed 300 micrograms per liter in some areas. The health effects of chronic arsenic exposure include skin lesions, cancers of the skin, bladder and lung, cardiovascular disease, and neurological effects. The arsenic contamination crisis in Bangladesh has been described as the largest mass poisoning in human history, and it illustrates the critical importance of understanding the geochemistry of groundwater in assessing its suitability for human consumption. The interaction between groundwater and geological structures, such as faults, folds, and unconformities, adds another layer of complexity to the study of the water table and subsurface hydrology. Faults can act as either barriers or conduits to groundwater flow, depending on the properties of the fault zone material. A fault that juxtaposes a permeable formation against an impermeable formation can effectively block the flow of groundwater across the fault plane, creating a groundwater dam that causes the water table to be at different levels on either side of the fault. Conversely, a fault zone that is filled with fractured and brecciated rock may have a higher permeability than the surrounding unfaulted rock, creating a preferential pathway for groundwater flow along the fault. The role of faults in controlling groundwater flow has important implications for well siting, contaminant transport, and the occurrence of springs and seeps. Folds, which are the bending or warping of rock layers by tectonic forces, also influence the distribution and movement of groundwater. Synclines, which are downward folding structures, tend to collect and concentrate groundwater in their axes because the dip of the permeable formations directs the groundwater flow toward the center of the fold. Anticlines, which are upward folding structures, tend to disperse groundwater away from their axes. The exploitation of groundwater in folded rock formations requires a thorough understanding of the geological structure, as the most productive wells are often those that are sited in the axes of synclines or at locations where the structural configuration of the aquifer concentrates the groundwater flow. Unconformities, which are surfaces of erosion or non-deposition that separate rock units of different ages, can also play an important role in groundwater hydrology. A weathered surface at an unconformity may have a higher permeability than the rock above or below it, creating a zone of enhanced groundwater flow along the unconformity surface. Alternatively, the accumulation of clay or other fine-grained material at an unconformity may create a low permeability barrier that confines the groundwater in the underlying formation. The water table in coastal environments presents a particularly interesting set of hydrological challenges. In addition to the problem of saltwater intrusion discussed earlier, coastal aquifers are subject to the influence of tides, which cause the water table to fluctuate in response to the periodic rise and fall of sea level. The amplitude of the tidal fluctuation in the water table decreases exponentially with distance from the coast, and the phase of the fluctuation is progressively delayed, so that the maximum water table elevation at a point inland occurs some time after the high tide at the coast. The tidal influence can extend several hundred meters to several kilometers inland, depending on the hydraulic properties of the aquifer, and it can have important effects on the mixing of fresh and saline groundwater in the transition zone between the two. In islands and narrow peninsulas, the freshwater lens that floats on the underlying saltwater is particularly vulnerable to depletion and contamination. The thickness of the freshwater lens depends on the width of the island, the rate of recharge, and the hydraulic properties of the aquifer, and it can range from a few meters on small, low-lying coral atolls to several hundred meters on larger, higher volcanic islands. On many small Pacific islands, the freshwater lens is the only source of drinking water, and its management requires careful monitoring of rainfall, pumping rates, and water quality to ensure that the lens is not depleted or contaminated by saltwater intrusion or surface pollutants. The role of groundwater in supporting wetland ecosystems is another aspect of the water table that has received increasing attention in recent decades. Many wetlands, including fens, bogs, marshes, and spring-fed pools, are sustained in whole or in part by the discharge of groundwater, which maintains the high water table that is essential for wetland vegetation and wildlife. The loss of wetlands due to the lowering of the water table by groundwater pumping or land drainage has been documented in many parts of the world, and it has led to the decline of many species that depend on wetland habitats, including amphibians, water birds, and a variety of aquatic plants and invertebrates. The recognition of the link between groundwater and wetland health has prompted efforts in many countries to protect groundwater-dependent ecosystems through the regulation of pumping, the establishment of buffer zones around sensitive areas, and the restoration of degraded wetlands through managed aquifer recharge and other techniques. The occurrence of groundwater in permafrost regions presents yet another set of unique challenges and phenomena. In areas of continuous permafrost, which is permanently frozen ground that extends from the surface to depths of several hundred meters, the movement of groundwater is severely restricted, and liquid water may be found only in unfrozen zones beneath large lakes and rivers, in deep formations below the base of the permafrost, or in thin active layers that thaw seasonally at the surface. In areas of discontinuous permafrost, where patches of frozen and unfrozen ground are interspersed, the groundwater system is more complex, with frozen zones acting as barriers to flow and unfrozen zones serving as pathways for groundwater movement. The thawing of permafrost due to climate change is expected to have significant effects on groundwater systems in northern regions, potentially increasing the connectivity between surface and groundwater systems, altering the patterns of recharge and discharge, and releasing methane and other greenhouse gases that have been trapped in the frozen ground. The deep subsurface, at depths of several kilometers below the water table, harbors a largely unexplored realm of groundwater that is fundamentally different from the shallow groundwater systems that provide the bulk of the world's water supply. Deep groundwater, also known as formation water or basinal brine, is often highly saline, with total dissolved solids concentrations that can exceed 300,000 milligrams per liter, which is nearly 10 times the salinity of seawater. The origin of this salinity is varied, and it may result from the dissolution of evaporite minerals, the concentration of seawater that was trapped in the sediments at the time of their deposition, or the membrane filtration of water as it is forced through clay-rich formations under high pressure. Deep groundwater has been found at depths of up to 12 kilometers in the Kola super deep borehole in Russia, the deepest borehole ever drilled, and it is estimated that the total volume of water stored in the upper crust of the Earth, to a depth of approximately 10 kilometers, may be as much as 110 million cubic kilometers, which is an order of magnitude greater than the volume of all the surface freshwater on the planet. In recent years, the discovery of microbial life in deep groundwater systems has opened new frontiers in the fields of microbiology and astrobiology. Bacteria and archaea have been found living in groundwater at depths of several kilometers, in environments that are completely isolated from sunlight and that have temperatures exceeding 100 degrees Celsius. These deep subsurface microorganisms obtain their energy not from photosynthesis, but from chemical reactions, such as the oxidation of hydrogen, the reduction of sulfate, and the metabolism of methane, that are driven by the geochemistry of the deep earth. It has been estimated that the total biomass of life in the deep subsurface may be comparable to or even exceed the biomass of all life on the surface of the Earth, though this estimate is subject to considerable uncertainty. The study of life in deep groundwater environments has important implications for the search for life on other planets, particularly Mars, where subsurface water may exist in conditions broadly analogous to those found in the deep terrestrial subsurface. The movement of heat by groundwater flow, known as advective heat transport, is another phenomenon that connects the water table and the broader groundwater system to processes of geological significance. In sedimentary basins, the flow of groundwater can significantly modify the distribution of temperatures in the subsurface, carrying heat from deep, warm formations upward and laterally toward discharge areas, where it emerges at the surface as warm springs or elevates the temperature of the soil and shallow groundwater. This process can have important effects on the maturation of organic matter in petroleum source rocks, the diagenesis and cementation of sedimentary formations, and the formation of ore deposits, in which hot, mineral-laden groundwater precipitates valuable metals such as copper, zinc, lead, and gold in veins and other structures. The study of ancient groundwater flow systems and their role in the formation of mineral deposits has been a productive area of research in economic geology. Many of the world's major ore deposits, including the Mississippi Valley-type lead-zinc deposits of the mid-continent United States, the copper deposits of the Zambian Copper Belt, and the uranium deposits of the Athabasca Basin in Canada, are believed to have been formed by the flow of groundwater through sedimentary basins over millions of years. In these systems, the groundwater dissolved metals from one part of the basin and transported them to another part, where changes in the chemical conditions caused the metals to precipitate and accumulate in economically significant concentrations. The study of these ancient groundwater systems, known as paleohydrogeology, requires the integration of geological, geochemical, and isotopic data to reconstruct the flow paths, temperatures, and chemical compositions of the waters that deposited the ores. Returning to the more immediate and practical aspects of the water table, the design and construction of wells for the extraction of groundwater is a topic of considerable engineering importance. Wells have evolved over thousands of years from simple hand-dug excavations to sophisticated engineered structures that can reach depths of more than a kilometer and produce water at rates of thousands of liters per minute. The basic components of a modern drilled well include the borehole, which is the hole drilled into the earth by a rotary or percussion drilling rig, the casing, which is a pipe inserted into the borehole to prevent it from collapsing and to seal off undesirable water-bearing zones, the screen, which is a section of perforated or slotted casing that allows water to enter the well from the aquifer while preventing the entry of sand and other fine particles, and the gravel pack, which is a layer of carefully graded gravel placed around the screen to improve the hydraulic connection between the well and the aquifer and to provide additional filtration. The design of a well, including the selection of the appropriate casing diameter, screen length, screen slot size, and gravel pack gradation, depends on the characteristics of the aquifer and the intended use of the well. and it requires a thorough understanding of the local hydrogeology. The development of a well, which is the process of removing fine particles from the aquifer material in the immediate vicinity of the well bore to improve its yield, is an important step in the construction of a new well. Well development techniques include pumping the well at a rate higher than its intended operating rate, surging the well by rapidly raising and lowering a plunger in the casing, and airlifting, in which compressed air is used to create a vigorous circulation of water in the well that dislodges and removes fine particles. A properly developed well will produce clear, sediment-free water and will have a higher specific capacity, which is the ratio of the pumping rate to the drawdown, than an undeveloped well in the same aquifer. The monitoring and management of well performance over time is also an important aspect of groundwater engineering. Over the course of its operational life, which may span several decades, a well may experience a decline in its yield due to a variety of processes, including the buildup of mineral deposits on the well screen and in the pore spaces of the aquifer near the well bore, the growth of bacterial biofilms that clog the screen and the surrounding formation, the migration of fine particles into the gravel pack, and the corrosion and deterioration of the well casing and screen. These processes, collectively known as well aging, can be mitigated through regular maintenance, including mechanical and chemical cleaning of the well, and through the rehabilitation of wells that have experienced significant declines in performance. The pumping of groundwater requires energy, and the amount of energy required depends on the volume of water pumped, the depth from which it must be lifted, and the efficiency of the pump and motor. The energy cost of groundwater pumping is a significant economic factor in irrigation, particularly in regions where the water table is deep or has been declining due to overpumping. In parts of India, for example, the cost of electricity for groundwater pumping is heavily subsidized by the government, which has contributed to the overexploitation of aquifers by reducing the economic incentive to conserve water. In other regions, the rising cost of energy has prompted farmers to adopt more efficient irrigation technologies, such as drip and sprinkler systems, and to shift to less water-intensive crops. The future of groundwater resources is a subject of considerable concern and uncertainty. The combined effects of population growth, urbanization, economic development, and climate change are expected to increase the demand for groundwater in many parts of the world, while at the same time potentially reducing the rate of natural recharge and increasing the vulnerability of aquifers to contamination and depletion. Climate change models predict that many regions will experience changes in the amount, intensity, and timing of precipitation, which will in turn affect the rate and distribution of groundwater recharge. In some regions, increased precipitation may lead to higher recharge rates and rising water tables, while in others, decreased precipitation or increased evapotranspiration may reduce recharge and accelerate the decline of water tables. The melting of glaciers and snowpacks, which are important sources of recharge for many aquifer systems in mountainous regions, is expected to alter the timing and volume of recharge. with potentially significant consequences for downstream water users who depend on the steady release of groundwater to maintain stream flows during dry seasons. The sustainable management of groundwater resources in the face of these challenges will require a combination of improved scientific understanding, better monitoring and data collection, more effective governance and regulation, and the adoption of innovative technologies and management practices. Among the most promising approaches are the expansion of managed aquifer recharge to store surplus water underground for use during dry periods, the development of more efficient pumping and irrigation technologies to reduce the demand for groundwater, the implementation of conjunctive use strategies that optimize the combined use of surface water and groundwater, and the strengthening of legal and institutional frameworks to ensure that groundwater is managed as a shared resource for the common good. As the night deepens and these considerations of the water table and the vast unseen reservoirs beneath the surface of the earth continue to unfold, one may contemplate the remarkable patience of groundwater, which moves so slowly through the darkness of the subsurface that a single drop of rain falling on a hilltop today may not emerge from a spring in a distant valley for hundreds or thousands of years. The water table rises and falls with the seasons, responding to the rhythms of rainfall and drought, of freezing and thawing, of pumping and recharge, in a ceaseless and largely invisible dance that sustains the rivers, the wetlands, the forests, and the cities of the world above. The minerals that dissolve in the water as it passes through the rock tell a story of geological time, of ancient seas and vanished mountains, of ice ages and interglacial warmth, a story that is written in the chemistry of every well and every spring. The porosity of the rocks through which groundwater moves is a reflection of their geological history, of the conditions under which they were formed, the forces that have acted upon them since their formation, and the processes of weathering and dissolution that have modified their structure over millions of years. A sandstone that was deposited in the channels of a braided river during the Cretaceous period, approximately 100 million years ago, may have a porosity of 15 to 25%, while a granite that crystallized from magma deep in the Earth's crust during the Precambrian era, more than 1 billion years ago, may have a matrix porosity of less than 1%. Yet both of these rocks may serve as aquifers, the sandstone through its intergranular pore spaces, and the granite through its network of fractures and weathered zones, each yielding water to wells and springs that serve the needs of human communities and natural ecosystems. The permeability of these rocks, which determines the rate at which water can flow through them, is equally varied and equally influenced by geological history. A well-sorted, clean gravel deposit may have a hydraulic conductivity of 1,000 meters per day, meaning that groundwater can flow through it at a rate of roughly 1 meter per day under a typical hydraulic gradient, while intact. Unfractured shale may have a hydraulic conductivity of less than 0.00001 meters per day, meaning that groundwater would take more than a century to traverse a single meter of this material. The enormous range of permeability values found in nature, spanning more than 12 orders of magnitude, is one of the factors that makes the study of groundwater flow both challenging and endlessly fascinating, though perhaps not in a way that would keep one awake. The water table itself, that invisible surface below which all the pore spaces are saturated, continues its slow undulations beneath the surface, rising and falling in patterns that reflect the interplay of climate, geology, and human activity. In some places, the water table is so close to the surface that one can feel the dampness of the soil underfoot, while in other places, it lies so far below the surface that one could drill for hundreds of meters without encountering a single drop of water. This variability is what makes the study of hydrogeology so complex and so essential, for the water that lies beneath the surface is, for billions of people, the difference between abundance and scarcity, between health and disease, between prosperity and hardship. And so the water moves, slowly and patiently, through the dark spaces between the grains of sand and the fractures in the rock, driven by the gentle but relentless force of gravity and the subtle differences in pressure that exist from one point to another in the subsurface. It moves from the hills to the valleys, from the highlands to the lowlands, from the areas of recharge where the rain falls to the areas of discharge where the springs emerge and the rivers flow. It carries with it the dissolved remnants of the rocks through which it has passed, the calcium and bicarbonate of limestone, the silica of sandstone, the iron and manganese of shale, creating a chemical record of its journey that can be read by those with the knowledge and the instruments to decipher it. The water table is not merely a line on a geological cross-section or a number in a well log. It is the upper surface of a vast, interconnected body of water that lies beneath the continents, a body of water that is in constant, if imperceptibly slow motion, flowing from areas of higher hydraulic head to areas of lower hydraulic head in obedience to the laws of physics that govern the movement of fluids through porous media. It is a resource of incalculable value, of a reservoir of fresh water that dwarfs all the lakes and rivers of the world combined, and it is a resource that is increasingly threatened by the competing demands of agriculture, industry, and domestic use, by the contamination that results from human activities, and by the uncertain effects of a changing climate on the patterns of recharge and discharge that sustain it. The study of the water table and the groundwater that lies beneath it is, in the end, the study of one of the most fundamental and most taken for granted aspects of the natural world. It is the study of water in its most hidden and most patient form, water that has seeped down through the soil and the rock, through the vadose zone and the capillary fringe, to join the great unseen reservoir that underlies the surface of the earth. It is water that may have begun its underground journey decades or centuries or millennia ago, and that may not complete that journey for decades or centuries or millennia to come. It is water that sustains the springs and the streams, the wetlands and the forests, the farms and the cities, in a continuous and largely invisible cycle of recharge and discharge that has been operating in one form or another for as long as there has been an atmosphere to produce rain and a lithosphere to receive it. The hydraulic properties of the aquifer materials through which this water moves can be characterized by a set of parameters that include not only the hydraulic conductivity and the porosity already discussed, but also the storativity, which describes the volume of water that an aquifer releases from or takes into storage per unit surface area per unit change in hydraulic head. In an unconfined aquifer, the storativity is approximately equal to the specific yield, which is the fraction of the total volume of the aquifer that can drain under the influence of gravity, and it typically ranges from about 0.1 to 0.3. In a confined aquifer, the storativity is much smaller, typically ranging from 0.00001 to 0.001. Because the water that is released from storage comes not from the draining of pore spaces, but from the slight compression of the aquifer skeleton and the slight expansion of the water itself as the pressure is reduced. This difference in storativity between confined and unconfined aquifers has important implications for the response of the water table or potentiometric surface to pumping. A given amount of pumping will cause a much larger and more widespread drawdown in a confined aquifer than in an unconfined aquifer, because much less water is released per unit decline in head. The transmissivity of an aquifer, which is defined as the product of the hydraulic conductivity and the saturated thickness, is another important parameter that describes the ability of the aquifer to transmit water over its full thickness. The transmissivity is particularly useful in the analysis of pumping tests and in the design of well fields, because it integrates the effects of both the permeability and the thickness of the aquifer into a single number. Aquifers with high transmissivity, such as thick, permeable sand and gravel formations, can support high pumping rates with relatively little drawdown, while aquifers with low transmissivity, such as thin, fine-grained formations or fractured crystalline rocks, can support only modest pumping rates and may experience significant drawdown even at low pumping rates. The specific storage of an aquifer, which is the volume of water released from or taken into storage per unit volume of aquifer per unit change in hydraulic head, is related to the storativity by the equation S equals SS times B, where S is the storativity, SS is the specific storage, and B is the thickness of the aquifer. The specific storage is a property of the aquifer material itself, rather than of the aquifer as a whole, and it depends on the compressibility of the aquifer skeleton and the compressibility of the water. For most geological materials, the specific storage ranges from about 0.000001 to 0.0001 per meter, with the higher values associated with more compressible materials such as clay and the lower values associated with less compressible materials such as sand and gravel. These parameters, taken together, provide a quantitative framework for describing and predicting the behavior of groundwater systems, from the response of a single well to pumping to the evolution of regional water tables over decades and centuries. They're the building blocks of the mathematical models that hydrogeologists use to simulate groundwater flow and transport, and they are the quantities that must be determined through field measurements and laboratory tests in order to apply those models to real-world problems. The field measurement of aquifer properties is typically accomplished through pumping tests, also known as aquifer tests, in which a well is pumped at a controlled rate and the resulting changes in water level are measured in the pumped well and in one or more observation wells located at known distances from the pumped well. By analyzing the pattern of drawdown as a function of time and distance, using the Tice equation or one of its many variants, the transmissivity and storativity of the aquifer can be estimated. The accuracy of these estimates depends on the quality of the data, the appropriateness of the analytical method, and the degree to which the actual aquifer conditions conform to the assumptions of the analytical model, which typically include the assumption of a homogeneous, isotropic, and infinite aquifer of constant thickness. In practice, of course, no aquifer perfectly satisfies these ideal assumptions, and the interpretation of pumping test data requires considerable professional judgment and experience. Aquifers are invariably heterogeneous, meaning that their properties vary from place to place, and they may be anisotropic, meaning that their properties vary with direction. They are bounded by geological features such as faults, formation contacts, and surface water bodies that limit their extent and influence their response to pumping. They may be partially confined, with leaky confining layers that allow water to seep slowly between adjacent aquifer units. And they may be unconfined, with the complicating factor that the saturated thickness of the aquifer changes as the water table rises and falls. All of these factors must be considered in the interpretation of pumping test data and in the construction of numerical models that represent the aquifer system. The field of hydrogeology has benefited enormously from advances in computing technology over the past several decades. The development of powerful personal computers and sophisticated software packages has made it possible to construct and solve complex three-dimensional models of groundwater flow and transport that would have been inconceivable a generation ago. These models can simulate the effects of multiple pumping wells, variable recharge and discharge, heterogeneous aquifer properties, and complex geological structures. And they can be calibrated against field observations to improve their predictive accuracy. The results of these models are used to guide decisions about well placement, pumping rates, aquifer protection, contaminant remediation, and water resource planning, and they have become an indispensable tool in the practice of modern hydrogeology. And with these considerations in mind, one might allow the thoughts of the water table to recede gradually, like the water table itself during a long dry season, settling quietly into the deeper layers of consciousness, where they may rest undisturbed. Much as the ancient waters of the Nubian sandstone rest undisturbed beneath the sands of the Sahara, waiting patiently for whatever may come next, whether it be the slow return of the rains, the gradual rise of the water table, or simply the passage of another unremarkable day in the long and unhurried history of the water that lies beneath the surface of the earth.